Good morning, students. Today we are going to discuss about aromatic hydrocarbons. There we will discuss meta-directing groups. Meta-directing groups. So, what are meta-directing groups? Let us see. Meta-directing groups, they are also called electron withdrawing groups or ring deactivating groups. Okay, electron withdrawing or electron attracting groups or ring deactivating groups. Now, let us say these electron attracting or withdrawing groups, that is atoms or group of atoms, will decrease the electron density in the benzene ring. They will decrease the electron density in the benzene ring. So the effect of substituents will decrease the electron density in ortho and para positions. Ortho, that is second and sixth position, and para is fourth position. So the newly incoming electrophile will be directed to meta position. Meta position, that is whenever electron withdrawing group or ring deactivating group or electron attracting group is present as the first substituent on the benzene ring, then what happens? It deactivates the benzene ring at ortho and para positions. At ortho, that is 2, 6, para in the sense fourth position. Thus, the electron density at these positions will be decreased. So, the newly coming electrophile will be directed to meta position by the already present group in the benzene ring. So, that's what these groups are called meta-directing groups, and electron density in ortho and para will be decreased, and the electrophile is forced to substitute at meta position where the electron density is slightly high or greater than ortho and para positions. So the rate of the reaction is very less, and the slow reaction is due to the ring deactivation by the already present electrophile. And these are also called the ring deactivating groups. These groups which deactivate the benzene ring at ortho and para positions are also called ring deactivating groups. And example for such type of groups, uh, first one is nitro group, and next one is trimethylamino group, and this is CF3 group, that is trifluoromethyl group, and this is cyanide group. And these are all the meta directing groups or ring deactivating groups. Now let's discuss about the reaction and different uh, groups. How do they affect the electrophilic substitution on benzene ring? Now here let's consider the general example. This is substituted benzene, monosubstituted benzene, where already Z is the ring deactivating group, which is already present on the benzene ring. Now the incoming electrophile, it has to go to the meta position, because at ortho position, that is 2 and 6 position, the para position, that is fourth position, the electron density is less. That is when compared to meta positions, here the electron density is less. Therefore, the incoming electrophile is forced to go to meta position only, either this or this. Okay, meta position. So thus we get a meta disubstituted benzene. Meta disubstituted benzene. And here the examples we have already discussed: NO2 group, trimethylamino group, CF3 group. These are all the meta directing groups or ring deactivating groups. Now, first of all, let's discuss about nitro group, which is a meta directing group. Nitro, NO2. NO2 or nitro group is an electron withdrawing group or electron attracting group. Electron attracting group. And it is a meta directing group, as the electron density in ortho and para positions is less. Therefore, electrophile has to go to meta position. Now, so this is about nitro group. Now, how this nitro group influence the incoming electrophile addition. So here, let us consider this nitrobenzene. Nitrobenzene. Now, the electrophile, if it goes to ortho, para, and meta positions. So what are the different resonance structures produced, and what is their stability? That we will discuss with the help of this reaction mechanism. Now this is nitrobenzene. Now electrophile, if it goes to ortho position, then at ortho position, with the help of this pi bond electrons, it forms a bond with the electrophile, newly coming electrophile. It forms a sigma bond with this particular carbon at ortho position. This we can see here, carbon and electrophile, a sigma bond is formed and the pi bond breaks, and here the adjacent carbon, it gets the positive charge. Now the positive charge on benzene ring is delocalized with the help of the remaining two pi bonds present in the ring. Okay, therefore what happens, we will get different resonance structures, and we know that as the number of resonance structures increases, the stability of that particular molecular ion also increases. So here let's consider, if this bond pair, if this pi bond electrons, if they go inside this side, then the positive charge will be on this particular carbon. Okay, now this pi bond electrons, they move this side, in between these two carbons, this positive charge will be on this particular carbon where NO2 group is attached. Okay, so this is unstable. This is unstable because the positive charge is present on the carbon to which nitro group is attached. Directly this nitrogen atom is attached. So this will make the structure very much unstable, as nitro group is electron withdrawing group. This nitro group is electron withdrawing group. So the positive charge which is present on this particular carbon to which NO2 group is attached, as this nitro group is withdrawing group, this structure becomes less stable. Structure becomes less stable or unstable. Okay, so in this particular attack, that is at ortho attack, we get a resonance structure where the carbon to which NO2 group is attached bears the positive charge. Thus, this particular structure is highly unstable. Highly unstable. And finally, we can show the loss of H plus from this particular sp3 carbon where electrophile is attached. Then the final product is obtained as ortho disubstituted product. Okay, now let us consider this one. This is meta attack. Meta, that is incoming electrophile goes to meta position. So when it goes to meta position, it forms a sigma bond with the help of pi bond electrons, one of the pi bonds from benzene ring, to form a sigma bond in between this particular carbon, that is meta carbon, and third carbon and this electrophile. Then the adjacent carbon, it suffers with a positive charge. Then this will be in delocalization, the positive charges in delocalization with the remaining two pi bonds of the benzene ring. Then other carbons, they get positive charge due to resonance or delocalization of the pi bonds with this positive charge. So here in this structure, this carbon that is at ortho position, positive charge is there. Okay, in this also ortho position, positive charge, in this para position, positive charge. Okay, so the now finally this is the sigma complex which loses a proton to the other part of the reagent to form the meta disubstituted product. Form meta disubstituted product, and we can see in this meta substitution or meta attack. Okay, no such type of unstable structure we can observe where there is no positive charge on the carbon to which NO2 group is attached. Therefore, this is more favorable attack when NO2 group is present as a first substituent on the benzene ring. Now let's consider the para attack. Here the electrophile, if it goes to para position, then what happens, it forms a pi bond, it forms a sigma bond with the help of the one of the pi bonds in the benzene ring. Therefore sp3 carbon is generated here, and the adjacent carbon suffers with a positive charge, and this positive charge is in delocalization with the rest of the two pi bonds. Thus the positive charge is stabilized, and we get the different structures where other carbons will be having positive charge. You can see here this carbon has the positive charge. In this structure, this carbon has the positive charge where this is the carbon to which NO2 group is directly attached. This is electron attracting group. Therefore, the positive charge on this carbon is increased Because of that reason, what happens? This ion is destabilized or unstable. This is unstable. In para attack, an unstable structure we come across, and here also in ortho attack also. Such type of unstable structure is not present in the meta attack. Okay, so finally, this sigma complex, it loses a proton to the other part of the reagent to form the final product as the para disubstituted product. Okay, now let us see the conclusion of this particular attack. Positive charge, this is charge. Positive charge located on the nitrogen group bearing carbon will make the structure unstable as nitro group is electron withdrawing group. But in meta attack, no such structure is observed. That's why electrophilic substitution prefers meta than ortho and para attack. So nitro group is a ring deactivating group with meta directing nature. This is what we have discussed with the help of the reaction mechanism. Now, let's consider another example, that is carboxylic acid group or carboxy group, COOH group, carboxy group. So this carboxylic acid group or carboxy group, this is also meta-directing group. It is also an electron withdrawing group. Electron withdrawing group. This group has minus I effect and mesomeric effect also. It has a minus I effect and mesomeric effect, that is M effect, which will make benzene ring poorer in electron density as it attracts the electron density from the benzene ring. The electron density on the benzene ring decreases. So due to this, it deactivates and the electrophile is attracted towards the meta position. Okay, deactivation is at ortho and para positions. Therefore, electrophile has to go to meta position when such type of electron withdrawing group is present as a first substituent on the benzene ring. Now, let's discuss the electrophilic substitution of benzoic acid. Benzoic acid, that is COOH group is present as a first substituent on the benzene ring. Then what happens to the other electrophile, that is the second electrophile, which has to go to either ortho, para or meta position. When this particular electron withdrawing group is present, the incoming electrophile is forced to go to meta position only, because at ortho and para positions the electron density will be decreased. Okay, now let us see the uh, uh, different resonance structures produced due to these particular three different types of attacks. Now, first of all, if the electrophile, if it goes to ortho position, see ortho position, this one is that this we can show here one particular ortho position we consider it is at second position. So with the help of this pi bond electron, it forms a sigma bond with the electrophile, and the adjacent carbon, it gets the positive charge, which is in, it is in, it, it undergoes delocalization. This positive charge undergoes delocalization with the help of the remaining two pi bonds present in the benzene ring. Thus, this positive charge is delocalized. In this particular structure, if the positive charge is present on third carbon. In the next structure, it is present on fifth carbon. In this structure, it is present on first carbon. Okay, as we have already said, this is the carbon to which COOH group is attached, which is electron withdrawing group. Therefore, the positive charge on this particular carbon is increased, and thus the structure becomes unstable. And finally, this particular sigma complex, it loses a proton to the other part of the reagent to form the final product as orthodisubstituted product, where electrophile has to is substituted at the second position. So this is not favorable, because here we have an unstable resonance structure during the attack of electrophile at ortho position. Now let's consider the meta attack. In this particular meta attack, what happens? The electrophile, it goes to meta position. This one, let me say. So here a bond is formed in between this particular carbon and a electrophile. Thus the other carbon, uh, next carbon to this sp3 carbon, it gets the positive charge, and this positive charge is alternatively present to this two pi bonds. Therefore it is delocalized. That is mesomeric effect. Because of that, what happens, this positive charge is delocalized, and in this structure it is present on second carbon. You can see this structure, another resonance structure where positive charge is present on sixth carbon, and due to this delocalization, and now in this structure the positive charge is present on the fourth carbon. And in all these structures, the positive charge is present on the different carbons except the first carbon where the COOH group is present directly attached to that particular carbon. So such type of structure in this meta attack we did not get. Therefore, this is stable form. Therefore, this is more favorable position for the incoming electrophile to attack. So finally, this one, it loses a proton, the sigma complex, it loses a proton to form finally the meta disubstituted product. Now let's consider the para attack. In this para attack, what happens? The electrophile, it goes to para position, forms a bond, sigma bond with this particular carbon with the help of the pi bond electrons. Thus, the adjacent carbon gets the positive charge, and it is in delocalization with the rest of the pi bonds in the benzene ring. Thus, the different carbon atoms, they get the positive charge. You can see here, this is the carbon which is directly attached to COOH group. It is bearing the positive charge. This COOH group is electron withdrawing group. You can see the arrow here. It is towards the COOH group. It withdraws electrons from this bond. Thus, the positive charge on this particular carbon increases and the structure is destabilized. Therefore, this is unstable structure, not favored. Therefore, whenever COOH group is present as the first substituent on the benzene ring, the incoming electrophile has to go to meta position only. This is the favorable position. Okay, so this is about COOH group. When it is present as a first substituent, the second substituent or second electrophile has to go to meta position, but not at ortho or para positions. You can see here the explanation. The positive charge on the carbon atom where carbonyl group, that is COOH group, carbon is attached, make the structure unstable. As COOH group is minus I group or minus M group, that is, it is electron withdrawing group. So it is strongly deactivating group and meta directing group. So the incoming electrophile is forced to go to meta position to give the final product. Third example for meta directing groups or electron the ring deactivating groups is nitrile group or cyano group, cyanide, CN minus. So cyano group here nitrile group or cyano group. Nitrile group is also a ring deactivating group. Cyano group, it attacks it attracts the electrons from the ring towards itself. So this group shows minus I effect and the minus M effect like COOH group. So as it decreases electron density in ortho and para positions, the incoming electrophile, it prefers meta position for substitution. Okay, now let us see the reaction mechanism for this group, cyano group. When this cyano group is present as a first substituent on the benzene ring, the electrophile, if it goes to ortho position, meta position, and para position, what are the different structures produced? Let us see. Now, first of all, let's discuss about ortho attack. If the incoming electrophile, if it goes to ortho position, you can see here sp3 carbon is generated, and new sigma bond is formed in between this particular carbon and electrophile at ortho position, and the adjacent carbon to this ortho position, it bears the positive charge, and which is in delocalization with the rest of the two pi bonds. Thus, the positive charge is delocalized, and we get different resonance structures or mesomeric structures, where the positive charge is present on different carbons here in the meta position, here meta position, here also meta position, this one fifth position, and in this first position, where to this carbon cyanide group is attached, which is electron withdrawing group. Therefore, the positive charge is increased. Thus, the structure becomes unstable. Therefore, this is not favorable position for the attack of second electrophile at ortho position, as there is an unstable resonance structure in this path. And finally, this loses a proton to form the disubstituted product, which is not favorable. And next, let us see the meta attack. Meta attack. In this meta attack, let's see what is that happening. The electrophile, it goes to third position. A new sigma bond is formed in between this carbon and electrophile. Okay, this ortho carbon or second carbon, it gets the positive charge, which undergoes delocalization. Then this particular carbon gets the positive charge, another ortho position. Okay, now if it is in delocalization with this pi bond, then the positive charge will be present on the para position. And finally, this carbon, it loses, this is meta carbon, and third carbon, it loses this proton. Then we get a meta disubstituted product. And in these structures, there is no positive charge on first carbon. You can see in all these structures, nowhere positive charge is present on the first carbon to which cyanide group is attached. Therefore, these are all stable structures. Therefore, the substitution at meta position is preferred whenever cyanide group is present on the benzene ring as a first substituent. Okay, now let's consider the para attack. It is similar to ortho attack. See, para position. Electrophile forms a sigma bond with this particular carbon. This carbon becomes sp3 hybridized, and the other carbon, the next carbon to this, it becomes positively charged, and this positive charge is in delocalization with the rest of the pi bonds in the benzene ring. And thus, a positive charge is delocalized in this carbon, in this structure. It is present on fifth carbon, in this first carbon, here it is in third carbon. So, and here is a less stable or unstable structure we can observe here, where the positive charge is present on the first carbon to which cyanide group is attached, which is electron withdrawing group because of minus I effect or minus M effect. Thus, this structure becomes unstable as the positive charge is increased. Thus, the para attack is also not favored when CN group is present on benzene ring initially. Therefore, ortho and para positions, where during this attack we can observe the unstable structures. Therefore, meta attack is more favored. So, cyanide group, it it also directs the incoming electrophile to meta position due to ring deactivation. Structures with cyanide carbon having positive charge are unstable, as cyanide group is minus I group. Okay, electron withdrawing group. So compared to ortho and para positions, meta is higher in electron density and gives stable structures. So nitrile group, that is cyano group, is meta directing and ring deactivating group. This point we should remember. Now let's consider another example, that is carbonyl group or aldehydes or ketonic groups when they are present as the first substituent on the benzene ring. Then what happens to the another substitution, another electrophilic substitution on that particular ring? So we can see here. So carbonyl group, that is COR, or this is ketonic group COR or CHO group, that is aldehyde group. So aldehydes and ketones are minus and minus I and minus M affecting groups. That is, they are also electron withdrawing groups or electron attracting groups. So these carbonyl groups, they withdraw electrons from the ring and deactivate it. So they deactivate the ring at ortho and para positions when compared to meta position. Therefore, the incoming electrophile has to go to meta position only. So due to which they act as meta directing groups. So this is pH means C6H5CHO benzaldehyde pH COR, that is it is a ketone, that is phenyl, and this is alkyl ketone. So the carbon of carbonyl group will become positively charged charged by the migration of electrons towards oxygen. And we know that the electron polarization, the bond polarization or the electron migration in carbonyl group is towards oxygen, as oxygen is more electronegative when compared to carbon. Thus this carbon gets the partial positive charge and this oxygen gets a partial negative charge. So further, it becomes the positive due to the resonant structures will make the structures unstable. So here what is that happening? Due to this bond polarization, carbonyl carbon will become positive by migration of electrons towards oxygen. And further, this positive charge is resonance stabilized due to the resonance structures. And in these resonance structures, we will come across in this reaction mechanism, we will come to know what is that happening to the carbon to which this CO and H are CO and R. COH means aldehyde, COR means ketone. Group is present on the benzene ring. So let us consider this. See, you can see here, this is aldehyde group or ketonic group or C double bond O group. When it is present on directly on the benzene ring, what happens to the electrophilic substitution? So the electrophile, if it goes to ortho position, okay, then at ortho position, a bond is formed, sigma bond is formed in between, new sigma bond is formed in between this particular carbon and the electrophile, and the other adjacent carbon gets the positive charge. It is delocalized with the help of the two pi bonds in the ring. So here the third carbon gets the positive charge in the other resonance structure, fifth carbon in the next resonance structure, first carbon. So to the first carbon COR group, this group is present. The C double bond O group is electron withdrawing group, minus I group. So minus I group or minus M group. Because of that reason, what happens? The positive charge on this particular carbon is increased. Thus, it becomes less stable or destabilized. So an unstable resonance structure we will come across when C double bond O group is present on the benzene ring during the electrophilic attack. Okay, so the meta attack, you can see such type of what do we say? Positive charge is not present in this. You can see positive charge is not present on first carbon atom in these structures in the meta attack. Okay, so because of that reason, meta attack is more favored and no unstable structure is present here. If we consider the para attack, okay, the para attack, you can see a new sigma bond is formed in between this particular para fourth carbon and electrophile, and the adjacent carbon bears the positive charge which is delocalized with the help of these two pi bonds. You can see here different resonance structures are produced, where in one resonance structures the carbon to which the C double bond O group is directly attached is bearing the positive charge. And we know that C double bond O group, that is ketonic group, is a carbonyl group, we mean to say ketone or aldehyde. Carbonyl group is a minus I group or minus M group, that is it withdraws electrons from this particular bond. Then what happens? The positive charge on this particular carbon increases and the structure is destabilized and an unstable structure is produced. Because of that reason, this is not favored. That is, the electrophilic substitution at para position is not favored, whereas ortho and para in both mechanism, both the paths, we can observe the unstable structure here, unstable structure. And in the case of meta attack, such type of unstable structure is not there. Therefore, meta attack is more favored whenever a carbonyl group is directly attached to benzene ring as a first substituent. That is, aldehyde ketone group is present as a first substituent. The incoming electrophile has to go to meta position because at ortho and para positions, the electron density is decreased. Electron density is decreased due to minus I effect or minus M effect of carbonyl group. And next group, that is sulfonic acid group, SO3H. Sulfonic acid is a meta-directing group due to minus I and minus M effect. That is, ring deactivation takes place due to this electron withdrawing or electron attracting capacity of this SO3H group, that is sulfonic acid group. So, the electron withdrawing nature of SO3H group makes less density of electrons in the ring. Okay. And this less electron density in the ortho and para position makes the electrophile to approach the meta position. So the electron density on the benzene ring at ortho and para positions is decreased. Therefore, the incoming electrophile, the second electrophile, it has to go to meta position whenever SO3H group, that is sulfonic acid group, is present as a first substituent on the benzene ring. Okay, now these are the different resonance structures. Okay, see here, this is benzene sulfonic acid, SO3H. The electron shift or bond polarization of SO bond towards oxygen, as oxygen is more electronegative than sulfur. Therefore, the bond polarization is like this, that is electron withdrawing nature. We can show it like this. And now the electrophile, if it goes to ortho position and para position, we get in the reaction mechanism, we can observe that one unstable structure is produced where the positive charge is present on the carbon to which directly SO3H group is attached, which is an electron withdrawing group. As it is an electron withdrawing group, then what happens? The positive charge is not delocalized or it is not reduced. Because of that reason, the this particular structure becomes less stable or unstable. Therefore, this is not the preferred path for the electrophilic substitution at ortho position. Similarly, para position also, we can observe this structure where the carbon to which SO3H group is attached is bearing the positive charge. Therefore, this is not the favored path for the second electrophilic substitution. Whenever SO3H group is present as a first substituent on the benzene ring. So therefore, you can see here in the meta attack, there is no positive charge on this particular carbon to which SO3H group is attached. Therefore, this is the more favored path, or we can say that whenever SO3H group is present on the benzene ring, at ortho and para positions, the electron density is decreased. At the ortho and para positions, the electron density is decreased. Therefore, the electrophile has to go to meta position. This is the more favored path. Okay. Now, so you can see here carbonium ion and the sulfur group are unstable. Carbonium ion and the sulfonic acid group are unstable in ortho and para resonance structures. Meta substitution is stable. That is this one we said. This is carbonium ion, this is carbonium ion, that is the in carbon bearing the positive charge. All these are carbonium ions. These are obtained. These carbonium ions in this ortho and para attack where the carbon to which SO3H group is attached are less stable. Because of that reason, whenever SO3H group is present on the benzene ring, the incoming electrophile has to go to meta position. That is, this one dictates the incoming electrophile to go to meta position only, because it is a ring deactivating group. Okay, next. Next, let's discuss about halogens. Halogens means that is general representation is X, which is equal to either chlorine or bromine or iodine. So these halogens, they have minus I effect, that is electron withdrawing effect, and which causes ring deactivation, but the plus M effect of halogens makes the electrophiles to attack on the ortho and para positions. So they have minus I effect as well as plus M effect. So due to plus M effect of these halogens, then what happens? The incoming electrophile has to go to ortho and para positions only. Ortho and para positions only. Okay. So let's show this. The lone pair on halogen activates the ring and acts as orthopara directing group. Because of this plus M effect, lone pair, it is uh, pushed towards the benzene ring. Because of that reason, if the ring is activated, when the ring is activated, the incoming electrophile has to go to ortho and para positions. Ortho and para positions. Okay. We can see this chlorine, when it is present on the benzene ring, that is chlorobenzene, we considered here as the monosubstituted benzene. And here, if the electrophile, if it goes to ortho position, what happens? Let's see. Okay. Now, the electrophile, with the help of this pi bond electrons, it forms a sigma bond with this particular ortho carbon, that is second carbon, and the adjacent carbon gets the positive charge. Okay, then what happened? Either this or this, no problem. In the other structure, positive charge here. So a positive charge, then what happens? The positive charge is delocalized with the help of the remaining two pi bonds. Then we get these structures, these different structures are produced. Now here, the positive charge is present on the carbon to which chlorine atom is attached. Okay, this chlorine atom is attached, and this chlorine, it has a plus M effect. Because of this plus M effect, what happens? A double bond is formed in between this carbon and chlorine. You can see the positive charge is delocalized with the help of this lone pair of electrons present on chlorine, and chlorine suffers with a positive charge. Okay. Now this bond shifts and this bond towards this, then this carbon gets the positive charge, the shift of bond towards this, then this carbon gets the positive charge, and finally this sp3 carbon loses a proton to the other part of the reagent. Then what happens? We will get a disubstituted product, that is ortho disubstituted product. The electrophile is present at ortho position. Okay. Now in these structures, you can see the positive charge on this particular carbon is stabilized, or it is delocalized by this chlorine due to its plus M effect. Therefore, it is the stable state. Next, let's see this meta attack. Meta position electrophile is forming a bond. This particular carbon gets the positive charge. Delocalization. This carbon gets the positive charge. Delocalization. This carbon gets the positive charge. And there is no positive charge on the first carbon. You can see no positive charge on the first carbon. Okay. So finally, this one loses a proton to give this product, and here no stable structure is present. Okay. Now, if we consider this para attack, The para attack, what is that happening? Um, Electrophile goes to para carbon, that is fourth carbon, forms a sigma bond. The adjacent carbon gets the positive charge, and this is stabilized by the remaining two pi bonds present in the benzene ring. Thus, the positive, if it comes over here, the positive charge is shifted to this particular carbon. You can see here, and this positive charge present on this particular carbon is uh, shared by the lone pairs present on the chlorine atom. Thus, this is only plus M effect. Due to this plus M effect of this particular chlorine atom, this carbocation is stabilized, and we will get this form where chlorine with a positive charge. Okay, this is the stable structure produced, and now the shift of this pi bond towards these two carbons and shift of this pi bond towards the chlorine atom, we will get a positive charge on this particular carbon. You can see here. Okay, now what happens? This particular carbocation, sigma complex, it loses a proton to other part of the reagent to form the finally para substituted product. Para substituted product is obtained. So in ortho and para substitution, we can come across stable carbocations here. This carbocation is stabilized by plus M effect of chlorine, and this carbocation is also stabilized by this one, stabilized by plus M effect of chlorine. Therefore, such type of stable structures are produced in this two parts. Therefore, whenever chlorine is present on the benzene ring as a first substituent, the incoming electrophile has to go to ortho and para positions. Ortho and para positions. Okay. So, though chlorine atom is ring deactivating group, this chlorine is ring deactivating group, but the electrophilic substitution is favored at ortho and para positions due to its plus M effect. Due to minus I effect, it is ring deactivating group. Due to plus M effect, the incoming electrophile goes to ortho and para positions than the meta position. Okay, than the meta position. Now, so here till now we have discussed about the different examples where we came across carboxylic acid, nitro group, nitrile or cyano group, then carbonyl group, that is aldehyde and ketonic group, and sulfonic acid group and halogens. These are all the groups which are ring deactivating groups, and they decrease the electron density on the benzene ring at ortho and para positions. Because of that reason, the electrophile goes to meta position. In the case of chlorine atom, though it is ring deactivating group, the incoming electrophile goes to either ortho or para positions because of plus M effect of this particular chlorine. So this is about the meta-directing groups. And here in this meta-directing groups, we will come across different questions like this. So the important questions of this particular topic are explain orienting influence of halogen in chlorobenzene. This one we should write. Explain orienting influence of halogen in chlorobenzene. So this particular answer we should write. And next one is about the what is that meta directing groups. So a ring deactivation, that particular question is also very, very important here. So what are benzene deactivating groups? How does this deactivation occurs? Justify your answer with the two examples. So here we have discussed many examples with chlorine, with the carbonyl group, carboxylic acid group, sulfonic acid group, nitro group. All this we can write any two examples. They have asked what are the benzene deactivating groups? How does this deactivation occurs? Justify your answer with two examples. So deactivation with two examples we should discuss. And next one is explain orienting influence of halogen in chlorobenzene. That is also another important question related to today's topic. Okay, and what else? That's all. These are the few questions we come across from this topic which we have already covered. Okay, right. Thank you. And we will continue the next topic in the coming session. Right. Thank you once again.